Today we will be talking about electron configuration. Let's start by very briefly reviewing what you've already learned about orbitals. An orbital is the region in the atom where an electron is most likely to be found at a particular energy level. We've talked about four different orbitals: the s orbital, the p orbital, the d, and the f. The s orbital is the lowest energy orbital. It can hold up to 2 electrons. Its shape is a sphere. The p orbital has higher energy than the s orbitals, has 3 orbitals, 2 electrons in each, and holds up to 6 electrons. These are the shapes of the p orbitals. Notice that they have that dumbbell shape, and there's one on each of those axes, the x, y, and the z. The d orbitals have higher energy than p orbitals. There are 5 orbitals with 2 electrons in each, and they hold up to 10 total electrons. Here are the shape of the d orbitals. The f orbitals have higher energy than d orbitals. There are 7 orbitals with 2 electrons in each, and they hold up to 14 total electrons. Here are the shape of the f orbitals. If you would like more information on these orbitals, I suggest watching the crash chemistry video also on my website about orbitals. Now, there are 3 rules that guide how electrons fill those orbitals. The first is the Aufbau principle. It says that electrons will always fill the lowest energy level first. The Pauli exclusion principle says that orbitals can only have at most 2 electrons. Hund's rule says that every orbital in a subshell is singly occupied with 1 electron before any one orbital is doubly occupied. And all electrons in singly occupied orbitals have the same spin. Here's what that means. We'll use the p orbitals to illustrate. In the p orbitals, there are 6 orbitals or 6 suborbitals, one along the z-axis, one along the y, one along the x. If I have an atom with full p orbitals, those electrons will first be placed one in each orbital, one in the z, one in the y, and one in the x. If there are more than 3, then another will be put in the z, another in the y, another in the x. Each orbital or suborbital gets 1 electron before any of them get a second. That's what Hund's rule means. Now, as far as spin, electron spin describes what we call the angular momentum of an electron. This diagram will help to illustrate. In this electron, you see that it is spinning in a counterclockwise direction. This electron shows it spinning in a clockwise direction. We describe the spin of electron as either being up or down, and you can see that with the arrows. When 2 electrons are in the same orbital, they cannot have the same spin because they will repel each other. One has to be up and the other has to be down. We represent the electrons in an orbital by showing them in a diagram that looks like this. Here we can see the up electron and the down paired in an s orbital. In the p orbitals, they are each placed one at a time in the orbitals. This diagram is incorrect because it does have the one up and the one down in the s, again with the s, but in the p it shows 2 being placed, one up, one down, in one in the next one, and the third orbital has none. Electrons would not do this. Each of these orbitals would have 1 electron before they would start to pair up. Let's talk electron configuration. Electrons always fill the lowest energy levels first. Electron configuration describes exactly how the electrons are arranged in orbitals around the nucleus. At the first energy level, the first s orbital gets filled. There are multiple s orbitals in an atom. Every energy level has its own s orbital. At the second energy level, we would see another s orbital, which you can see right here with this blue circle, and then the p orbital coming in on top of that. If we were to go to a third energy level, we would see another s orbital encompassing that, more p orbitals, and some d orbitals. You can start to see how this picture of an atom and the electrons can start to get quite complicated, and why we call it an electron cloud. In your worksheet, you have a table that looks like this. I'm going to walk you through filling out the first 3 rows of the table, and then I want you to fill out the 4th row by yourself. First, the column is the principal energy level. We just number those, starting with 1 is the lowest, The next highest would be 2, and the next highest would be 3. In the first energy level, there is only an s orbital. The s orbital only has one sublevel, so there's only one orbital in the first energy level. There are only 2 electrons in that s orbital, and we show that for a total number of electrons of 2. That first energy level can only have 2 electrons. Now we designate these orbital energy levels with the letter n. Another way of calculating total orbitals per principal energy level is n squared. You can see if n is 1, n squared is also 1. Another way to calculate total number of electrons per principal energy level is 2n squared. If n is 1, n squared is 1. 2 times that would be 2. At the second energy level, we have another s orbital and a p orbital. There's only one s orbital, but there are 3 p orbitals. Total number of orbitals, 3 plus 1 is 4, or n squared. 2 squared is 4. Total electrons in the s orbital is 2. Total electrons in the p orbital is 6. We can add those together, 6 plus 2, to get 8 total electrons in the second energy level, or 2n squared. 2n squared is 2, squared is 4, times 2 is 8. In the third energy level, there's an s orbital, a p orbital, and here we also start to get our first d orbitals. The s orbital, there's only one of them. There are 3 p orbitals, and there are 5 d orbitals. Total number of orbitals, 5 plus 3 plus 1 is 9, or we could do 3 squared, that's also 9. There are 2 electrons in the s orbital, 6 electrons in the p orbital, and 10 electrons total in the d orbitals. Remember, 2 in each. 5 times 2 is 10. If we add that up, 10 plus 6 plus 2, we get 18. Or we could do 2n squared. N is 3, n squared is 9, times 2 is 18. This diagram shows the energy levels and the order of energy from lowest energy to increasing of those principal energy levels. Starting at the bottom, you'll see the 1s orbital, that yellow circle with 2 electrons. Each of those arrows, remember, represents an electron, one with the up spin, one with the down. Notice that there won't be 2 up or 2 down in any of those circles. The next higher energy after 1s is actually the 2s orbital, and then 2p with its 3 orbitals, 3s, 3p, 4s. Then we get our first d orbitals with the 3d. Notice that there are 5. There are 5 orbitals in the d orbitals. 4p, 5s, 4d, 5p, 6s, and then 4f. Notice that there are 7 circles in the 4f orbitals. Then 5d, then 6p. We'll talk more about this order of energy levels in a minute. You also have this diagram on your worksheet. This gives you a graphic representation of the order of filling those orbitals. If we write the s orbitals from the first energy level down to the 7th, 1s down to 7s, there are 7 energy levels because there are 7 periods on your periodic table. And we'll relate this to the periodic table in a minute. Then 2p down to 7p, 3d to 6d, 4f to 5f. Then if we draw diagonal lines going from right to left through each of those, the order of filling the orbitals follows the order of the diagonal lines. First 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. This diagram just shows those principal energy levels, which we label with n. Here's n equals 1, 2, 3, and 4. Remember, those orbitals are where there is a high probability of finding an electron. When we write electron configurations, we will use this notation. This first number tells us the principal energy level. The letter tells us the orbital type, where those electrons are found, and then the superscript number tells us how many electrons are in that orbital. This would be the first energy level, the s orbital, and 2 electrons in that orbital. The periodic table can also give us a guide for the order of how electrons fill these orbitals. As we read across from left to right, we start with the 1s orbital with hydrogen and the helium. They only have electrons in that 1s orbital because they only have 1 electron and then 2. Going down to period 2, we have 2s, and then moving across, we get to 2p, then 3s, then 3p, then 4s, and then 3d. And if you're following along on your worksheet, you'll notice that this is the exact same order of filling with those arrows. Notice once we get to the first d orbital, even though this 3d is in the 4th period, it's the 3rd energy level. The d orbitals, the way to determine what energy level they're in, you do the period that they're in minus 1. So we start the 4th period with 4s, then 3d, then 4p, then 5s, then 4d, then 5p. Once we get down here to 6s, remember the lanthanides and actinides fit right in here. That's the F block. The F block starts with 4f. 4f would come in here right next to 6s. The way the F block works is you take the period it would be in minus 2. So any element on this lanthanide series, its final electrons would be in the 4f orbitals. On the back side of your worksheet, you have this table. I'm going to walk you through filling out the electron configuration for a few of these elements, then I'll have you do the rest on your own. Starting with magnesium, you're going to want to fill in the atomic number for each of these elements. The atomic number for magnesium is 12. Remember, there are always the same number of protons as electrons in a neutral atom. If there are 12 protons for the atomic number, then there are also 12 electrons. Let's see how those 12 electrons would fit in the orbitals. The first 2 would go in the 1s orbital, and notice they are paired. One was spin up, one was spin down. The next 2 would go into 2s orbitals. The next would go in the 2p, but remember there are 3 orbitals in the p orbitals, so we would have 3 groups of 2 or 6 total. Then 3s, and that takes us to a total of 12 electrons. 2, 4, 4 plus 6 is 10, plus 2 more is 12. Now, to write the electron configuration, we just write there are electrons in the 1s, we write 1s. There are 2 electrons, so we put the superscript 2. The 2s has 2 electrons, the 2p has 6 electrons, and 3s has 2 electrons. This is the electron configuration for magnesium. Let's skip down to chlorine. Chlorine has 17 protons. Its atomic number is 17. That means it has 17 electrons. The first 2 would go into 1s, the next 2 into 2s, the next 6 would go into 2p, the next 2 into 3s. That gets us to 12 electrons, so there's 5 left. Those 5 would go into 3p. To write the electron configuration, we have 2 electrons in 1s, 2s has 2 electrons, 2p has 6 electrons, 3s has 2 electrons, 3p has 5. I can check if I'm right by adding these superscript numbers. Remember, these numbers represent how many electrons. I should be able to add them up and get to a total of 17. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. Let's do argon. Argon has 18 electrons. 2 and 1 go in the 1s orbital. The next 2 go in the 2s orbital. The next 6 go in the 2p orbital. The next 2 go in the 3s. And the last 6 go in the 3p orbital. My electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6. Again, I can add up these superscripts and I should get 18 electrons. The last one I'm going to do with you is iron. Iron is number 26. It has 26 electrons. First 2 go into 1s, the next 2 into 2s, the next 6 go into 2p, the next 2 go into 3s, the next 6 go into 3p, then we have 2 and 4s, and here we get our first electrons going into the 3d orbitals. We have 6 going into 3d. Now, I could write out the entire electron configuration of iron, but you'll notice I'll be writing the same thing as I wrote for argon for those first 18 electrons. You can imagine that writing this out every time for every atom could get very tedious. So there is an abbreviated version. The abbreviated version uses the electron configuration for the noble gas that comes before that element. The noble gas that comes before iron is argon. And you put that noble gas symbol in brackets. What this is saying is, I'm showing that this is argon and that everything in those brackets represents the electron configuration for argon. But instead of writing it out, I'm just going to put argon in brackets. Then I'm just going to do the electron configuration that comes after. So iron, sorry about this bar coming up, I can't seem to get it to go off. Argon, everything is the same up to right here, this 3p. The only ones I need to add are 2 in the 4s orbital and 6 in the 3d. So I write 4s2, 3d6, and that's the abbreviated version. I could do the abbreviated version for magnesium, chlorine, and argon as well. Magnesium, the noble gas that comes before it, is neon. I would put neon in brackets and then 3s2 because those are the only other electrons that come after. Neon's electron configuration is 1s2, 2s2, 2p6. So I just need to add these last 2 electrons. The abbreviated electron configuration for chlorine, again, neon, 3s2, 3p5. Notice the only additional electrons after magnesium are these 5 in the 3p. Argon, if I want to do argon, the noble gas that comes before argon is neon again, 3s2, 3p6. Now, an easier way to figure out this electron configuration is using that periodic table. Remember, we showed that the periodic table can show us the order of our orbitals as we read from left to right. If I want to find the electron configuration for aluminum, I can find aluminum on the periodic table right here. If I come up here, starting with hydrogen, I have 1s. And in the 1s, I have 1, 2 boxes. That gives me 1s2. The next is 2s. In 2s, I have 2 boxes, 2s2. Moving across, the next one I get to is 2p. 2p has 1, 2, 3, 4, 5, 6 boxes, 2p6. Continuing on, 3s, 2 boxes, that's 3s2. And aluminum starts my 3p, and it's the first box. The final is 3p1 for aluminum. And it works out. Aluminum is element number 13. It should have 13 electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 1, plus 1 is 13. I could do the abbreviated by finding the noble gas that comes before aluminum. It's neon, put it in brackets, then just do what comes after, 3s2, 3p1. Now let's find the electron configuration for manganese. Manganese is right here. It's a transition metal. If I start up here, 1s, 1, 2, 1s2, 2s, 1, 2, 2s2, 2p, 1, 2, 3, 4, 5, 6, then 3s2, then 3p6, then 4s2, and now I get to the row, my first 3D with manganese. So I'm going to count 1, 2, 3, 4, 5. Manganese ends with 3d5. If I add up those electrons, it will add up to the total number of electrons in manganese. I could write the abbreviated for manganese by finding the noble gas that comes right before it. That's argon. and then just doing the configuration after argon. 4s2, 3d5. This can help us also figure out, if I give you an electron configuration, what element is it the configuration for? What is the element with the configuration of krypton, then 5s2 and 4d9? Well, I just have to find krypton right here. What comes after is 5s2, 4d9. I just count over 9 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the electron configuration for silver. Remember, down here on the lanthanides and actinides, we have 4F and 5F. The worksheet that I want you to do is the practice electron configuration worksheet. I want you to try writing those electron configurations, the full electron configurations, and then writing the abbreviated. Then practice identifying which elements have those electron configurations. You will be tested on this. The answers are on the back for you to check yourself. Some of the elements utilize the F orbitals. If you are feeling comfortable, go ahead and try these. If not, I would maybe skip these. You want to make sure you're comfortable with elements at least in the first 5 periods.